Hi everyone, so we're here on topic 8.4, acid-base reactions and buffers. I would recommend that you have watched topic 8.5 before this, just to get an idea of what those titration curves look like. So this first little part, I'm going to have you go ahead and list the strong acids and the strong bases. Don't forget, you can get that from topic 8.1/8.2. You do need to know those, so go back through and go get them. This first question, 10.0 milliliters of 1.00 molar HCl is titrated with 10 milliliters of 1.20 molar NaOH. So this one is going to be a strong acid and strong base. So go ahead and label that for yourself somewhere in here. So like we're going to do a bunch of different categories. So like this section right here, make a note and make it obvious that it's strong acid plus strong base. All right, so the balanced chemical equation, we have HCl plus NaOH produces, so that H connects with the OH, the Na connects with the NaCl, so we've got HOH, that is a liquid, and NaCl aqueous. We also know that it's going to be like the NaCl is also going to be the spectator ion. So if we want the net ionic for this, it's really H plus and OH minus is producing H2O. So if we think about what this reaction is between, it's between a strong acid and a strong base. So if we recall back from topic 8.5, and also if you were able to do a titration curve in 4.6, we would have over here would be our pH. Over here would be moles of NaOH added, or just even OH added. That says moles of OH added, I promise. You know you're going to have a fairly low pH. It's going to be horizontal like this. So go, 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 and then jump up and then level off. So right over here is your equivalence point. That's when your moles of OH are equal to your moles of H+. So these, we're going to do a bunch of things in these. So buckle up and make sure you got plenty of snacks with you right here. So we're trying to figure out the pH of this resulting solution, meaning that when we're adding these things together, what is the concentration at, what is the, like, do we have excess H plus? Do we have excess OH minus? If we have excess of either one of them, by how much is it? And so therefore, what would that pH be? So follow the steps with these. For strong acids and strong bases, the first step is to figure out the concentration. So determine concentration of the H plus and OH minus after we have mixed them together. And okay, so let's start with our H plus. So for H plus, we can say that we have 0.0100 liters of HCl, and I'm just getting this from the data right above, right over here, times 1.00 moles of HCl over 1 liter. And we should have, let's see, 1 mole of H plus for every 1 mole of HCl. I know it doesn't seem to matter because it's just a 1-to-1 ratio, but sometimes you'll have more than a 1-to-1 ratio. So you want to make sure that we get that all figured out. So this is equivalent to 0.010 moles of H plus. But we also have to think about what's going to happen after we have mixed it together. So we have 10 milliliters of HCl plus another 10 milliliters of NaOH. So overall, we're going to have 20 milliliters of the total volume. So here we can say it's 0.0200 liters of the total solution. So when you have that, calculate that out, there should be 0.50 molarity of the H plus. we'll do the same exact thing for the OH minus. We know we have 0.10, whoopsies, there's a 0 in front of that, 0 liters of NaOH. So 0.0100 liters of NaOH times, and then its concentration is 1.20 moles of NaOH for every 1 liter of NaOH. And then I know I have 1 mole of OH minus for every 1 mole of NaOH. And so calculating that out, it looks like it is 0.0120 moles. Yeah, looking at moving those over. Okay, cool. Moles of OH minus over 0.0200 liters of the resulting solution, because you've added those two solutions together. So that should give you 0.60 molar OH minus. Cool. So we figured out what is the concentration is of H plus and OH minus after mixing. Now we have to figure out, hey, how much is combined up with water? And like figuring out what's binding with water, and then the leftover is going to be what we're going to use to figure out our pH. So we're going to use something called a BCA table to determine excess after making water. So we know our net ionic is H plus OH minus produces H2O. These are similar to rice tables, slightly different. Like the B is the before, the C is your change, and your A is after. So again, pretty similar to your rice tables, but again, before, change, and after. Or we would have done like initial, change, and equilibrium. We just want to make sure that we realize that this is not a rice table because we're not a system at equilibrium. This is a system that is going to go to just like one direction. So let's take a look at what we have from above. From step 1, we figured out we had 0.50 molar H plus. OH minus, we had 0.60 molar H plus. We're going to kind of ignore water here. Now, we just have to look at which one do we have less of, i.e. which one's the limiting reagent. So since we had less H plus and more OH minus, that means the OH minus is your excess and your H plus is your limiting reagent. So we're going to say 0.50 molar. We're going to subtract that out from each one of those. We have 0 H plus left over, and we have 0.10 molar OH left over. So then, because this is a strong acid, strong base, we can use the pH square. And when I say pH square, I mean go back to topic 8.1, 8.2, and look at this. In fact, make this like on as like one of your like put it on colored paper and make sure that you have this readily available as we're progressing through this unit. So we're going to use the pH square to determine the constant, or the pH itself, right? So since we have excess OH minus, we have this, we need to get to here. So follow a path. And again, it could be across and down or down and across, does not matter. I just feel like doing POH is equal to the negative log of your OH concentration. So my POH is equal to the negative log of 0.10 molar. And when I get that, that should be a pH of, or excuse me, well, a POH of 1, my bad. So that's my POH. And then I can use that to say that my pH is equal to 14 minus my POH. So 14 minus 1 gives me 13. So let's make sure this makes sense. If I have excess of a strong base when mixed after a strong acid, I should have a fairly high pH. So yeah, that makes sense. That checks out. Cool. All right, so that's fairly straightforward. The only new thing here might be like the BCA table, but again, not too difficult. Taking a look at our next one, here we have 10 milliliters of 1.200 molar HC2HO3. That's titrated with 5 milliliters of 0.10 molar NaOH. Looking at this is not on our list of strong acids, so this must be a weak acid. And this is a strong base. So this page, label as, and depending on which side your staple is on, maybe I'll do it right over here. This whole page is going to be a weak acid plus a strong base. Okay, so balanced chemical equation. We are taking HC2HO3 plus NaOH. That H is going to combine. So you have HOH and NaC2HO3 in there. This will be a system at Na is just going to be your one spectator ion. So actually we can even get rid of that. Oh, let me just do that over here. So HC2HO3 plus OH minus is in equilibrium. So this is a system at equilibrium. I meant to say that earlier, my bad. And you have C2HO3 minus. So notice that we're not getting rid of like this here because this is a weak acid. It's not going to be completely disassociated, so you're going to have some of this as well as some of this left over. So it's not like with HCl where the Cl was also going to be a spectator. If we're titrating these two together, we expect that we have a pH that might be like fairly low, essentially, here when we're titrating these. So we've got this is our equation. This reaction is between a weak acid and a strong base. So think back to when we were doing the titrations, when we had a weak acid and strong base. I'm going to go back up to number 4 when I was doing this with topic 8.5. Note that we had a little bit of a dip right over here, or a little bit of like a hook, essentially. I don't even know if hook's the right thing to say in here, but we had our pH. We had our moles of OH added. It kind of curved up a bit. Then followed the same thing, but this pH was going to be like around 3. And that equivalence point ends up being greater than 7. So now we have to determine the the pH of this resulting solution. So we're going to do the first step that we did in the previous one, where we figure out the concentrations of OH minus and your H plus after mixing. So go back to your previous question, right? Like we showed you how to do that. Ideally, you would pause right here and go through and figure that out. And as I'm talking right now, that means that you have unpaused or you've played and you've already figured out all this stuff, ideally, right? So your OH minus, it is your H plus, my bad, 0.0100 liters of your HC2HO3 over 1. And then we are mixing that, we're making 0.200 moles of HC2HO3 over 1 liter of HC2HO3. And then we know we have 1 mole of H plus for every 1 mole of HC2HO3. So that gave us, going across, 0.00200 moles of H plus And then I want to know what my final solution is. So I've got 10 milliliters and 5 milliliters. So that's 15 milliliters. 15 milliliters in liters is going to be 0.01500 liters. Let me just double check. Oh, that's just that one. Okay, cool. Doing this, I am not going to do mental math here. 0.002, what's these? 0.02 divided by 0.015. Cool. 0.133 repeating, and that's your molarity of H plus. All right, we're going to do the same exact thing for OH minus. I want you doing that same exact thing for OH minus. When you get that, you will find that it ends up being 0.033 molar OH minus. If you did not get that, rework it or talk to other people. If a combination of you guys didn't do it and there's something I may have messed up on, let me know. But I'm pretty sure that that ends up being the correct answer for that. All right, step 2, use the BCA table. So we're going to use our net ionic equation. So HC2HO3 plus OH minus is in equilibrium with water and our weak conjugate base. Cool. And BCA, the before, the change, the after. We know water is not usually a part, or anything that's a liquid or solid is not part of our equilibrium expression. So here we started out, I just gathering the data that I had from up here, 0.133 molar, and this is 0.033 molar. And we just find out whichever one's limiting. So in this case, it's the OH that's limiting. It's a smaller number. 3 molar. So this ends up being 0. That looks like it is 0.100 molar. And we also have to think about what's happening here. If we're taking away 0.033 molar over here on the left-hand side, we're adding it over to this side. So we're starting out with 0 here because initially there's none of this ion. So here we have 0.033 molar. So it looks like our weak acid is in excess. So let's make sure we make a note. Weak acid is in excess. Before, when I had said in topic 8.5, hey, you're going to find that you have an excess weak acid. Use something called the Henderson-Hasselbalch equation. You'll do that in topic 8.4. We're in topic 8.4. So here we're going to say we're going to use the Henderson-Hasselbalch. I am really apologizing profusely if I misspelled that. So use this equation because the weak acid is in excess. All right, this equation. So it is found in your reference table. It's the pH is equal to pKa plus the log of your conjugate acid or conjugate base, over your weak acid. Right? So again, it's the pH is equal to the pKa plus the log of your conjugate base over your weak acid. So my pKa was given to me right up here. 3.18 plus the log of, and let's label these, right? So this is my HA. This is my A minus. So the log of 0.033 over 0.100. And remember, do the log part first and then add in your pKa. So I'm going to do log of 0.033 divided by 0.1 equals plus my pKa, 3.18. So that gave me 2.1 let's say 2.7 as my pH. And again, I had to use this because I had a weak acid in excess. All right. So moving on, 100 milliliters of 0.100 molar of acetic acid. So let's think about acetic acid. That is also going to be, think back to see if it's a strong acid or a strong base. So acetic acid ends up being a weak acid. It's added to 100 milliliters of 0.100 molar potassium hydroxide, which is a strong base. So let's make sure that we have this noted in here. So we have weak acid plus the strong base. Balanced chemical equation, we always want to start with those. We have HCH3COO plus KOH. Potassium is a group 1 metal. Group 1 metals are always soluble, so therefore this will be a spectator ion. So we end up with, let's see, if we're going to kind of switch these two. Sorry, let me switch them for you guys, and then we'll do the net ionic. So we have KCH3COO plus the HOH, but showing the net ionic, we have HCH3COO plus the OH minus is in equilibrium with CH3COO minus plus your water. I'll write water out like that. So this reaction is between a weak acid and a strong base. So kind of going back to our previous one, pH, we have our moles of OH minus. There's going to be a little bit of a dip and like that. So that pH is going to be greater than 7. This pH right over here is around a 3. So we got to figure out what we have here. First step, we're going to figure out the concentration of H plus and OH minus. Do that exactly like we did before. When you find that, you will find that your concentration of H plus is equal to 0.0500 molar, and your OH minus is equal to 0.0500 molar OH minus. So you end up having equimolar of each of these. So let's go ahead and write in here. Your concentration of H plus is equal to your concentration of OH minus. So this is what to do when you see this. If that happens, then you move over to your BCA table. You end up with, let's see, HCH3COO plus OH minus in equilibrium with CH3COO minus plus H2O. Set up your BCA. It seems like a moot point because you kind of know what's going to go on in here, but I just need to show you mathematically, and you also need to show your AP graders when you're doing this. So you have 0.0500 for each of these. This one you're starting out with 0. You're going to subtract out 0.0500 from each side. And over on this side, you add in 0.0500. So here you have 0. That's 0. But this is 0.0500. Okay, you got that part. Now, this then needs to go into a rice table. So this step is a rice table. Do the rice table exactly like you've been doing before, except this time you're starting out with this as your initial. Let's see, rice. So I'm switching the order of my products and reactants here, and I can do that because it's in equilibrium. So I have CH3COO minus plus H2O in equilibrium with HCH3COO plus OH minus. And let's talk theory behind this as I go through this real quick. It's in equilibrium, right? So yes, we know that you don't have any more of this left over, but you do know that there's still going to be some that goes in the reverse direction. So that's what you're trying to figure out. And 0.0500 minus B, this is B, this is B. Cool. Throw it into a KB expression. And hopefully you realize that, hey, we needed to really know unit 7 really, really well in order to be successful here. Well, that's multiplication. That shouldn't be addition. All right. So always do your K expression. Make sure that's in there. Your KB. Ooh, I'm given a pKa, not given a KB. So I got to go back through. I have to remember that pKa plus pKb is equal to 14. So my pKb in here, ooh, that was rough, is 14 minus whatever my pKa is, which is 4.74. Subtract those two, make that obvious. Not mental mathing this. 14 minus 4.74 is 9.26. Cool, that's my pKb. Now I need to find my kb. So my kb is equal to the negative, that should be the 10 to the negative pKb. So 10 to the negative 9.26. Definitely not doing mental math with that. Negative 9.226. Cool. So that is 5.495. That looks like 5.50 times 10 to the negative 10th for my KB. All right, coming back over here. 5.50 times 10 to the negative 10th is equal to, let's see, we've got B in this one, B in that one, so that's B squared. And then 0.0500 minus B. Go ahead and say, assume B is negligible. And so you end up with B being, and I'm just going to do this math real quick. Please do the math so that we can kind of go through this. Let's see. So when you get that, you end up with your B being 5.24 times 10 to the negative 6th molar. And we know that's also our concentration of OH minus. This one's the pH. So, actually, let me do concentration of OH minus. So, figure out the concentration of H plus. I know there's so many steps here, isn't it? But it's kind of like rewarding when you have to do a problem that's multiple pages or like a big page like this. I promise you, it's rewarding. So OH minus times H plus is equal to 1.0 times 10 to the negative 14th. So your H plus concentration is equal to, that in the calculator, 1.91 times 10 to the negative 9th. And since that's your H plus concentration, hey, throw that into negative log of your H plus concentration. Negative log of 1.91 times 10 to the negative 9th. And that's equivalent to log of 1.91 negative 9, sorry, 8.72. Whew. So that's your pH is equal to 8.72. And let's see, does this make sense? You had a weak acid. Let me get this over here. Your weak acid, it's being titrated with a strong base. Your pH out of the equivalence point should be above a 7. And that's what we end up having, above a 7, which ended up working beautifully. All right. I would love to say that we're done. We're not done. There's still some more stuff that we need to do. Take a look at this one. We have HClO2. Let me just make sure I get this. Yeah, so HClO2. This is going to be a strong acid. This is actually one of our strong acids. And MgOH2, this ends up being a strong base. Um, Actually, I'm going to pause right here on our video. My bad. I just want to make sure I pause it right here and then we will come back to this in a bit. Take care.